Right. I hope my voice is audible and the video is visible. Good evening, everybody. We will be studying GATE today, and yeah. So regarding the GATE, we have studied programming in C, and we have studied the data structures, and now it's time to study algorithms, right? So we will not be looking at the charts until we complete the entire algorithms. It is as simple as that. The asymptotic analysis of algorithms is a critical topic for GATE graduate aptitude test in engineering, especially for candidates in computer science and related fields. The set of notes provides an in-depth understanding of how algorithms behave as input size grow and is fundamental for assessing their efficiency. Let's delve into an algorithm for these nodes. The word algorithm means a set of rules to be followed in calculations or other problem solving operations, or a procedure for solving a mathematical problem in a finite number of steps that frequently involves recursive operations. Therefore, algorithm refers to a sequence of finite steps to solve a particular problem. Algorithms can be simple and complex depending on what you want to achieve. Input: set of rules to obtain the expected output from the given input. Output: types of algorithms: brute force, recursive, backtracking, searching, sorting, hashing, divide and conquer, greedy, dynamic programming, randomized algorithm. Asymptotic notations in mathematics. Asymptotic analysis, also known as asymptotics, is a method of describing the limiting behavior of a function. In computing, asymptotic analysis of an algorithm refers to defining the mathematical foundation of its runtime performance based on the input size. For example, the running time of one operation is computed as f of n, and maybe for another operation it is computed as g of n square. This means the first operation running time will increase linearly with the increase in n, and the running time of the second operation will increase exponentially when n increases. Similarly, the running time of both operations will nearly the same if n is small in value. Usually, the analysis of algorithm is done based on three cases: best case, omega notation. Okay, I did not sign in. Wait. That's why things are looking different actually. Where is this dark mode? Mhm. How to enable? Yeah, here. Nice. And we have a high comfort. Okay. Best case omega notation, average case theta notation, worst case O notation. So f of n equals to omega of g of n if there is positive constraints n naught and c such that the right of n naught, the f of n always lies on or above c into g of n. Okay. Okay, to the right of n naught. All right. So as you can see here, after n naught, this f of n is always greater than c of g of n. That's what he is trying to say. Theta notation: f of n is equal to theta of g of n if there are positive constraints n naught and c such that to the right of n naught, and not the f of n always lies on or above c1 into g of n and below c2 into g of n. So it is like a Bollinger Band. If you are into stock market, this is the lower band, and this is the upper band, and this is the middle band. You can sort of say that. Big O notation: f of n is equals to O of g of n if there are positive constants n naught and c such that the right of n naught, the f of n is always lies on or below c into g of n. So it is exactly opposite of omega notation. Yep. Worst case is like the bottom part, best case is like the top part. Alright. Asymptotic analysis given two algorithms for a task how do we find out which one is better? One naive way of doing this is to implement both the algorithms and run two algorithms on your computer for different inputs and see which one takes less time. There are many problems with this approach for the analysis of algorithms. It might be possible that for some inputs the first algorithm better than the second, and for some inputs the second performs better. It might also be possible that for some inputs the first algorithm performs better on one machine and the second one works better on another machine for some other inputs. Asymptotic analysis is a big idea that handles the above issues in analyzing algorithms. In asymptotic analysis, we evaluate the performance of an algorithm in terms of input size. We don't measure the actual running time. We calculate how the time or space taken by an algorithm increases with the input size. Measurement of complexity of an algorithm worst, best, and average case based on the above three notations of time for complexity. There are three cases to analyze an algorithm. Worst case analysis, mostly used, denoted by big O notation. In the worst case analysis, we calculate the upper bound. Okay. So this is G of n. Okay. We calculate the upper bound on the running time for an algorithm. We must know that that causes the maximum number of operations to be executed. For linear search, the worst case happens when the element to be searched x is not present in the array. When x is not present, the search function compares it with all the elements of array one by one. Therefore, the worst case time complexity of the linear search would be O of n. Best case analysis is rarely used, denoted by the omega notation. In the best case analysis, we calculate the lower bound on the running time of an algorithm. We must know that the case that causes a minimum number of operations to be executed. In the linear search problem, the best case occurs when x is present at the first location. The number of operations in the best case is constant, not dependent on n. So the time complexity in the best case would be omega of 1. Average case analysis rarely used, denoted by theta notation. In average case analysis, we take all possible inputs and calculate the computing time for all the inputs. Sum all the calculated values and divide the sum by the total number of inputs. We must know or predict the distribution of cases. For the linear search problem, let us assume that all the cases are uniformly distributed, including the case of x not being present in the array. So we sum all the cases and divide by the sum by n plus 1, because we must also include the case of not being present in the array, so that adds 1 to the number of observations. Following is the average case time complexity. How to analyze loops for complexity analysis of algorithms? Constant time complexity O of 1. The time complexity of a function or set of statements is considered as O of 1 if it does not contain a loop, recursion, or call to any other non-statement time function, i.e. the set of non-recursive and non-loop statements. In computer science, O often refers to constant time complexity, which means that the running time of an algorithm remains constant and does not depend on the size of the input. This means that the execution time of an O of one algorithm will always take the same amount of time regardless of the input size. An example of an O of one algorithm is accessing an element in an array using an index. Linear time complexity O of n. The time complexity of a loop is considered as O of n if the loop variables are incremented or decremented by a constant amount. For example, following functions have O of n time complexity. Linear time complexity, denoted as O of n, is a measure of the growth of the running time of an algorithm proportional to the size of the input. In an O of an algorithm, the running time increases linearly with the size of the input. For example, searching for an element in an unsorted array, or iterating through an array and performing a constant amount of work for each element would be O of n operations. In simple words, for an input of size n, the algorithm takes n steps to complete this operation. The operation. Quadratic time complexity of n power c. The time complexity is defined as an algorithm whose performance is directly proportional to the square of the input size. As in nested loops, it is equal to the number of times the innermost statement is executed. For example, the following sample loops have n of n square time complexity. The loops are not given, and here also something is missing. Here, I guess. Here, for example, following functions have of n time complexity. What are the following functions? It was not copy pasted properly. Who wrote this article? Okay. Why? Copy paste anyways, but he provided us with something to read. Quadratic time complexity denoted by of n square refers to the algorithm whose running time increases proportional to the square of the input size. In other words, damn it. In other words, for an input size and the algorithm takes n times n steps to complete the operation. An example of an O of n square algorithm is a nested loop that iterates over the entire input of each element, performing a constant amount of work for each iteration. The result in a total n times n iterations, making the running time quadratic in the size of the input. Logarithmic time complexity O of log n. The time complexity of a loop is considered as O of log n if the loop variables are divided or multiplied by a constant amount. And also for recursive calls in the recursive function, the time complexity is considered as O of log n. Uh, wait, wait. This is not making sense. Um, this is not an accurate statement, right? Because if the recursion happens n times for an input of size n, then it will be O of n, right? This happens when the problem size is reduced by a factor for each recursive call. Each recursive call halves the input size. Okay, that works. Yeah, factorial. Fibonacci, linear recursion. Recursion is not inherently O of log n, it can be O of n or even exponential, right? Exactly. So should I report this one? The quality of the article is not good. How to report it? Because the quality of the article is not good. Seems like the contents were copy pasted from another resource, and that copy pasting was not done accurately. For example, in some sentences it was written the following function has of n time complexity, and the code for function is not present. And also in the O of log n section, it was told recursive functions have a time complexity of O of log n. It is not true because there exist recursions that have linear and exponential time complexity as well. Please define the change in the article since it is since it plays a significant role in the understanding of algorithms. I don't know if anyone's going to read that or not, but I should do it. Where are we? Oh, one of n power 0 of login. Wait, where was I reading? Yeah, here, right? Logarithm time complexity it should be only one of log n, not log n. Okay, wait. There is something called log of log n. The time complexity of a loop is considered as O of log n if the loop variables are reduced or increased exponentially by constant amount. How to combine the time complexities of consecutive loops? Do we have something called okay, okay, finding the highest power of two Van Emde Boss trees. Van Emde Boss tree. Okay. Yeah, it's I don't know. I have no idea. Amortized analysis. How to combine the time complexities of consecutive loops? When there are consecutive loops, we calculate the time complexity as the sum of the time complexities of individual loops. To combine the time complexities of consecutive loops, you need to consider the number of iterations performed by each loop and the amount of work performed in each iteration. The total time complexity of the algorithm can be calculated by multiplying the number of iterations of each loop by the complexity of iteration and taking the maximum of all possible combinations. Here, the outer loop performs n iterations and the inner loop performs m iterations of for each iteration of the outer loop. Okay, so the total number of iterations performed by the inner loop is n times m, and the total time complexity is O of n times m. N times I guess. Here, the outer loop performs n iterations and the inner loop performs I iterations for each iteration of the outer loop, where I is the current iteration count of the outer loop. The total number of iterations performed by the inner loop can be calculated by summing the number of iterations performed in each iteration of outer loop, which is given by the formula sum of I is equals to sum of I from I is equal to 1 to n. Uh, okay, wait. I is the okay. So if the value of I is okay. So this I and this I are same. They are not two different variables of different ranges. The range of I is dynamic. It depends on this variable. Okay. N into n plus 1 by 2, that is a formula for counting the sum of numbers. Nice, because 1 plus 2 plus 3, that is correct. It is making sense, alright. Algorithm cheat sheet for complexity analysis, runtime analysis of algorithms. In general cases, we mainly use it to measure and compare the worst case theoretical running time complexities of algorithms for the performance analysis. The fastest possible running time for any algorithm is often commonly referred to as constant running time. In this case, the algorithm always takes the same amount of time to execute regardless of the input size. This is the ideal runtime for an algorithm, but it's rarely achievable. In actual cases, the performance runtime of an algorithm depends on n, that is the size of the input or the number of operations is required for each input item. The algorithms can be classified as follows from the best to worst performance: running time complexity. A logarithmic algorithm of log n runtime grows logarithmically in proportion to n. A linear algorithm, a superlinear algorithm, a polynomial, an exponential, a factorial algorithm. Little o and little omega notations. Big O is used as a tight upper bound on the growth of the algorithm's effort. The effort is described by a function f of n. Even though, as written, it can also be a loose upper bound. Little o notation is used to describe an upper bound that cannot be tight. Definition: let f of n and g of n be functions that map positive integers and positive real numbers. We can say that f of n is O of g of n if for any real number constant c is greater than 0. Where is c in this case? Okay, if for any real constant c greater than 0, there exists an integer constant n not greater than 1 such that thus, little o means loose upper bound. Little o is a rough estimate of the maximum order of growth, whereas big O may be the actual order of growth. Okay, little o and little omega. The relationship between omega and little omega is similar to big O and little o, except that now we are looking at the lower bounds. Little omega is a rough estimate of the order of growth, whereas big omega may represent the exact order of growth. We use little omega notation to denote a lower bound that is not asymptotically tight. Let f of n and g of n be functions that map positive integers to positive real numbers. We say that f of n is omega of g of n if for any real constant c greater than 0 there exists an integer constant n not greater than 1 such that f of n is greater than c of g of n is greater than 0 for any integer n greater than n naught. Greater than 0. Okay, because it is lower bound. Uh, is the definition of little omega correct? Especially the inequality because is it mandatory for the values to be less than 0. Alright. Both are assumed to be positive functions, so inequality is about growth comparison, not about negativity. Okay, f of n grows at least as fast as g of n. The inequality in the definition is not about being less than zero, it is about being greater than every constant multiple of g of n beyond some threshold. So the definition you wrote is essentially correct, except the phrase mandatory for values to be less than zero is a misunderstanding. The condition is about positivity and domination, not negativity. Okay, that kind of makes sense because there is no mandatory for the lower bound to be smaller than zero all the times. F of n has a higher growth rate than g of n, so main difference between big omega and little omega lies in their definitions. In the case of big omega, f of n is equals to omega of g of n. The bound 0 is less than c of g of n is less than or equal to f of n. But in case of little omega, it is true. Okay. What does space complexity mean? We almost completed the topic, people. The term space complexity is misused for auxiliary space at many places. Following are the correct definitions of auxiliary space and space complexity. Auxiliary space is the extra space or temporary space used by an algorithm. The space complexity of an algorithm is the total space taken by the algorithm with respect to the input size. Space complexity includes both auxiliary space and space used by input. For example, if we want to compare standard sorting algorithms on the basis of space, then auxiliary space would be a better criterion than space complexity. Merge sort uses O of an auxiliary space, insertion sort uses and heap sort. Insertion sort and heap sort uses O of one auxiliary space. The space complexity of all of these sorting algorithms is O of n though. Okay. Space complexity is a parallel concept to time complexity. If we need to create an array of size n, this will require O of n space. If we create a two-dimensional array of size n times n, this will require O of n square space. In recursive call, stack space also counts. Int add int n if n is less than or equal to 0, return n plus add of n minus 1. So the recursion calls n times makes sense. However, just because you have n calls does not mean it takes O of n space. That is true. Add sequence int n in sum is equal to 0 for I is equal to 0, I less than n. So pair sum function is being called. This will roughly be O of n calls to pair sum. However, those calls do not exist simultaneously on the call stack, so you only need O of n space because alright. The pair sum is being called and it is not calling itself again, so it will just return a value and it will be stored in sum and gets incremented. So and there is no recursion call in add sequence. Nice, nice. That's a good analysis. We are not touching PYQs at this moment, right? We completed the first article. Now we did not get any charts. All right. Okay, we completed all of this and. Recurrence relations, divide and conquer, greedy algorithms, graph algorithms, dynamic programming, searching, sorting, technique-based theorem, and hashing. Okay, that is not very terrible. Master theorem is something that needs to be understood, though. Yeah, not too bad. Okay, so yep, until here. So master theorem is a complicated and important topic. Recurrence relations are the mathematical backbone of algorithmic analysis. providing a systematic way to express the time complexity of recursive algorithms. As GATE Exam 2024 approaches, a profound understanding of recurrence relations becomes imperative for tackling questions that demand a deep comprehension of algorithmic efficiency. These notes aim to present a concise and illuminating guide to recurrence relations, covering key concepts and techniques that are likely to be assessed in the GATE examination. All right. Uh, Let me drink some water. So this, yeah, yes. A recurrence relation is a mathematical expression that defines a sequence in terms of its previous terms in the context of algorithmic analysis. It is often used to model the time complexity of recursive algorithms. What is linear recurrence relation? In a linear recurrence relation, each term is a sequence of its linear combination of previous inputs. General form. Alright. F of n is a function. How to solve recurrence relations? The analysis of the complexity of a recurrence relation involves finding the asymptotic upper bound on the running time of a recursive algorithm. This is usually done by finding a closed form expression for the number of operations performed by the algorithm as a function of input size and then determining the order of growth of the expression as the input size becomes large. Wait, this sentence is kind of big. This is usually done by finding a closed form expression for the number of operations performed by the algorithm as a function of the input size, number of expressions. Okay, that is that is what was asked. Yeah, number of operations, and then determining the order of growth of the expression as the input size becomes large. Yeah, what he is trying to say is if there are n calls and each call has a loop in it, then it wouldn't be O of n, it would be much more than that because in every recursive call you are having a loop. And even worse, if you have a nested loop in each recursive call, then that will be even worse, right? Because in recursion, every function acts as a separate function itself and it will have its own memory for variables and all. Right. We make a guess for the solution and then we use mathematical induction to prove the guess is correct or not. Substitution method, okay. For example, consider the recurrence t of n is equal to 2 tn by 2 plus n. We guess the solution is n log n. Now we use induction to prove our guess. N log n. Alright. We need to prove that. Alright. Okay. Is this a valid inference? Because you can guess too high sometimes. Is this a valid inference? Because it might be just not analog. How are you going to prove that height upper bound is O n log n but not O of log n just by this logic? Mm-hmm. This grows. Okay, wait. We T of n is less than 2 times C n by 2 log n by 2. C of n log n. Okay. Have not understand mathematical thought behind it. Maybe I need to have some mathematical play with this. Mhm. Think, okay, recurrence tree method. At the root, cost is equal to n. At the next level, two subproblems of size n by 2 each contributes cost n by 2. Every level contributes exactly n work. The recursion stops once the problem. Okay. Recurrence tree method. Alright. In this method, we draw a recurrence tree and calculate the time taken by every level of the tree. Finally, we sum the work done at all levels. To draw the recurrence tree, we start from the given recurrence and keep drawing till we find a pattern among levels. This pattern is typically arithmetic or geometric series. This seems more intuitive to be honest. So this is a given recurrence relation and okay, so this is the base case Cn square you can say. T of n by 4 is called and n by 2 is called. If we further break down the expression T of n by 4, okay. So T of n by 4, if you substitute n by 4 here, you will get n by 4 that is n by 16, okay, and n by 8. And how did you get this? C n square by 16, yeah, by 16, okay. No, how can you say this is by 16? The value of T of n, we need to calculate the sum of tree nodes level by level. Alright, to know the value of T of n, we need to calculate the sum of tree nodes level by level. To know the value of T of n, we need to calculate the sum of tree nodes level by level. If we sum the above tree level by level, we get the following series. Okay, it is a geometric progression. I mean, you can kind of see this and say like this takes n times and this takes n times, and this is O of n square. But that will be just a guesswork, right? And can you say that here? Here this takes log n times and this takes n times, but here, okay, we already have an n square. That is like the majority term. Master method is a direct way to get the solution. The master method works only for the following types of recurrences or for recurrences that can be transferred into the following types. T of n is equal to a into T of n by b plus f of n. There are the following three cases. The master method is mainly derived from the recurrence tree method. If we draw the recurrence tree of T of n is equal to a t n by t plus f of n, we see the work done, the root is f of n, and the work done at all levels is theta of n power c, where c is log a to the base b, and the height of the recurrence tree is log n to the base b. Okay. He is trying to get some proof from the recurrence tree method. So, uh, so the master method is derived from the recurrence method, recurrence tree method. I need to get into a position in mathematics where I can intuitively derive the proof behind it. Formalization of the intuition you get from the regression tree method. Let us connect the dots. So, the recursion tree gives intuition, work per level into depth. The master theorem packages that intuition into a neat formula so you don't have to rederive it each time. That is the entire philosophy behind the math formula, so that you don't rediscover the wheel. And it is not being told like that. In the recurrence tree method, we calculate the total work done. If the work done at leaves is polynomically more than leaves or the dominant part, and the result becomes the work done at leaves. Case 1. If the work done at leaves and root r is asymptotically the same, then our result becomes height multiplied by the work done at any level. Case 2. If the work done at the root is asymptotically more, then our result becomes work done at the root. Case 3. Wow. It is already you are getting an intuition in the mind, but you cannot formalize it. That is it. Examples of some standard algorithms whose time complexity can be evaluated using the master method. Okay, it was given for merge sort and binary search. Notes, it is not necessary that a recurrence is of the form T of n is equal to a t n by b plus f of n can be solved using master theorem. It is not necessary. Okay. This gives three cases having some gaps between them. For example, the recurrence T of n is equal to 2T n by 2 plus n by log n cannot be solved using the master method. Case 2 can be extended. Okay, so you need to understand this, not just have the proof. Alright. Yeah, recurrence is something that you must have an idea about. But anyways, let's read it. Where are we? Yeah, here. Advanced master theorem for divide and conquer recurrences. The master theorem is a tool used to solve recurrence relations that arise in the analysis of divide and conquer algorithms. The master theorem provides a systematic way of solving recurrence relations of the form T of n is equal to a t n by b plus f of n, where a, b, and f of n are positive functions and n is the size of the problem. The master theorem provides conditions for the solution of the recurrence to be in the form O of n power k for some constant k, and it gives a formula for determining the value of k. The advanced version of master theorem provides a more general form and the theorem that can handle recurrence relations that are more complex than the basic form. The advanced version of the master theorem can handle recurrences with multiple terms and more complex functions. It is important to note that the master theorem is not applicable to all recurrence relations and it may not provide an exact solution to a given recurrence. However, it is a useful tool for analyzing the time complexity of divide and conquer algorithms and provides a good starting point for solving more complex recurrences. Master theorem is used to determine running time of algorithms, divide and conquer algorithms in terms of asymptotic notations. Consider a problem that is solved using recursion. Function f is having an input x of size n, and if n is less than k, solve x directly and return. So if it is the value of n is below constant level k, then you can solve x directly. As divide x into a subproblems of size n by b, call f recursively to solve each subproblem, combine the results of all subproblems. Okay, actually that's why our teacher told master theorem along with the divide and conquer. She did not explain all of this though, but she kind of wrote down the formula on the board. If I'm if I remember it correctly, yes. The above algorithm divides the problem into A subproblems, each of size n by b, and solves them recursively to compute the problem of the extra work done for problem is given by f of n, i.e. the time to create the subproblems and combine the results in the above procedure. So according to master theorem, the runtime of the above algorithm can be expressed as t of n is equal to a tn by b plus f of n. Oh wait, the formula for advanced master theorem was not given, right? So this is the advanced. Okay, this is the advanced master theorem, I guess. Anyways, okay, not all recurrence relations can be solved using the master theorem. T monotone. Okay, it is not a polynomial. It is not a polynomial because it is having a variable power. The theorem is an advanced version of master theorem that can be used to determine running time of divide and conquer algorithms. If recurrences are the following from ATN by b plus theta into n power k log p log p to the base n, I guess. Okay. Okay, this is some mathematics and you need to solve it to understand. Divide and conquer recurrence relations, linear recurrence relations, value substitution before solving. Alright, as we have told, this is a complicated topic. So we came into divide and conquer, people. Yeah, 47 minutes. I see. So is it? Are they the same? So if you click on these things, they expand. Okay, you got code for these. You need to be good at coding as well, my guy. Yeah, that's true. The preparing of graduate aptitude test in engineering exam in 2024 faced many algorithmic challenges. Okay, it is 8:10 already. Let me eat and start the stream again. So, yeah, bye people, and I will continue the stream in like 30 minutes or something.